come for the panel and now for the talk, which I'm very curious about. So thank you very much. And I think, Jacob, you can take it over now. Welcome.
Great, thank you. So my name is Jakob Foerster. I'm a research scientist at Facebook AI Research, and I will be an assistant professor at the University of Toronto and the Vector Institute in Canada. And I'll talk to you about self-play and zero-shot human AI coordination in Hanabi. And I've put this human AI and in Hanabi here in brackets because I will talk about these things in those examples, but this idea of zero-shot coordination is relevant both when you have humans in the loop and when you don't have humans, when you're coordinating with other AI agents. And also those ideas they will be explored and illustrated here in Hanabi, but they're pretty generally universal. They're relevant whenever you have coordinating and competing, cooperating agents in this world. The structure of the talk is as follows. So I first talk about a little bit of like why I think we should study multi-agent learning. It's going to relate to the discussions we had in the panel session. Then I'll introduce the idea of theory of mind and the Hanabi challenge. And then in the first content part, I'll talk about self-play and the Bayesian action decoder, which is this idea of how to address multi-agent learning in fully cooperative partially observable settings. And then in the part two, I will get to what I think are those exciting new frontiers of multi-agent learning, which is zero-shot coordination and our solution algorithm mechanism other play. And that in particular lets us to actually develop policies that can coordinate with humans in Hanabi. Now, I've given this talk a number of times, so I'd be slightly bored at some point. So if you have questions, just ask them. I don't know what the right mechanism here is, but I would appreciate a more interactive presentation, because otherwise you can just watch a YouTube video. Without further ado, let's get started. Why should we study multi-agent learning? And first answer, the obvious real-world applications. Doesn't matter whether you think about communication networks, the Internet of Things, drones in the sky, robots in the warehouse. These are settings where you have a number of decentralized agents that get local observations and have to take local actions and want to accomplish something together in the world, right? So for example, these robots, these drones might only be able to observe a small patch of land, and they somehow have to coordinate to then rescue this poor victim that got stranded in the desert. What's important here is in many of these settings, we can do something that's called centralized training with decentralized execution. So while we're training policies in the simulator, we can actually train using centralized state information, such as the exact position of each of these drones in the world, as long as we don't require that state information at execution time. The second answer is that, we may have to interact with humans and other agents, right? And those is particularly important, for example, in traffic. So if you look at Waymo, they recently, I have to say, realized that the interactive situations such as merging will demand simulating other human, again in brackets, traffic participants, which they say is a rich area of ongoing research. And indeed, if you look at the failure cases that happen here, there was a journalist that followed this Waymo car, and the van took 1 minute and 23 seconds before they managed to change lanes, even in moderate traffic. While this is a huge failure, it also leads to amusement. So for example, this Twitter user was laughing tears when this Waymo car tried to get onto the highway and didn't manage because there wasn't any space for the car. Obviously, there isn't much traffic going on. So why didn't this car manage to merge? That's because they don't think multi-agent. Right? So fundamentally, if you assume that the other agents are studying in their behavior and aren't going to respond to your actions, then there simply isn't enough space to get onto the highway. You have to assume that when I take an action, I will create space on the highway by other agents reacting to my actions. And this idea that other agents have points of views, are going to react to my actions, that are strategic, is absolutely crucial when we think about self-driving cars. And that's a multi-agent problem in that sense. But I'm going to push this a little bit farther, which is that sort of almost all machine learning applications deployed in the real world then become multi-agent problems because there are other machine learning algorithms or human users in that real world. So here's an example that's maybe not obvious from the beginning, but think about machine translation, where you think about a training data set in the traditional view that consists of English sentences and you map into French. That's just a supervised learning problem from X into Y. Whereas the multi-agentness, well, what about the right-hand side, these users? In particular, one thing these users might want to do is they may want to translate their websites using your machine translation problem. And surprise, suddenly you will train on the training data, right? And in Google's credit, they actually noticed this. So what they said, a daunting new challenge, machine-generated structured results contaminate the pool of naturally generated human data. So what I'm illustrating here is really the moment you deploy a machine learning system, that thing is going to interact with the real world, and the real world contains other machine learning agents or human users. And that fundamentally makes most machine learning a multi-agent problem, whether we want it or not. So supervised problems exist, but they're fairly limited. They're those where you have, you're predicting the structure of atoms, or you're predicting, who knows, the solar flares of the sun, where there's no feedback loop. The moment you deploy something, give it to a human, it's going to be a multi-agent problem. Here's another example. So we have these algorithmic decision makers on Amazon, where we have two sellers. The first seller is competing on price. The price is set just below the cheapest competitor from the previous day. And there's a second seller that sets the price just above the most expensive competitor, 27% above. Both of these are fantastic strategies if you want to sell books and be the cheapest, or if you just want to compete on quality, you can afford to be the most expensive. And they work again quite well if I assume that other prices are more or less stationary and static, are sort of like natural prices. But what happens when seller 1 and seller 2 are the only two sellers that are selling a given book on Amazon? Does anyone have any guesses? What's the next slide in this setting? It's also a test if anyone's still listening.
They explode the price.
Okay, how do they explode?
Because seller 1 lists a book, and it sets the price just below the cheapest competitor. Okay, well, if there's only like if only these guys are selling books, or like a single book, seller 1 sets it just below Bordy book, and then the next day Bordy book says it 27 above him, and then seller 1 says it like just point 1 below, and so on.
I think this is the first time that I get a good answer to this question. Thank you very much. That's exactly right. This is called exponential growth. It grows at something like 26 point, whatever percentage every day. And it meant that this book on flight genomics was being sold for something like $24 million on Amazon. And it's not like at this point, the algorithm recovered common sense and decided this was stupid. No, it's the people writing blogs about this. And ultimately the human had to intervene and then turn off the algorithm. Right. So what this shows you is really having algorithmic decision makers, having other strategic agents in the environment fundamentally can change the kind of results we obtain when we do relatively simple things. But there's another answer here. That is that multi-agent learning has also been the road to the only human level intelligence systems that we know. So it might just be a, human level intelligence. I don't want to use the word AGI because I think that's too loaded and conflated. But human level intelligence came out of a multi-agent problem. And there's actually a little bit of like correlation evidence here. If you look at the mean group size in non-human primates on the y-axis on the log scale, and you look at the neocortex ratio. So what fraction of the brain is in the neocortex? And the neocortex is responsible for higher order reasoning, abstraction, yada, 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 yada. You see this very interesting correlation here where really, it seems like higher order reasoning is associated with living in a multi-agent context. And if you now think about putting humans on that same plot, obviously we now coordinate in a group that's much, 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 much larger than any other complex species. Right? We now coordinate something like billions of humans through our various innovations around multi-agent nature. Answer 5 here sets an easy way to create hard problems, right? I think it's really important as machine learning scientists that we keep challenging ourselves, and we want to spend as little time as we can on creating the problems, more time on solving the problems. And I'm always fascinated by the iterative prisoners dilemma. You have 4 numbers here, and you specify very, very simple dynamics, and yet there's 20,000 papers written on the prisoners dilemma. I myself published on it in 2017, and you get this infinite diversity of rich solutions that happen when you have intelligent agents that are interacting to solve what look like relatively simple problems on the surface. I should have added agent-based modeling, one thing I'm very excited about, but I forgot that here in the answers. So let's add the 6th answer here. I think many machine learning problems are naturally framed as multi-agent systems, right? So it doesn't matter whether you think about like GANs on the left-hand side, hierarchical reinforcement learning, where you have some higher level policy that communicates with lower level policies, or model-based where you have a policy to model. We have different loss functions and we have different parts of the model. And that is just the perspective that lets us solve these issues, these problems more effectively, right? So then moving on, 7th answer, I think it's a lot of fun. So multi-agent learning, I think, has this really rich problem space where we come across really deep insights, and there's a lot of fundamental work to be done. And I just prefer that to tuning hyperparameters on a well-established benchmark. possibly. Cool. So without further ado, let's talk about theory of mind. What do I mean by that? So imagine you're cycling down a road and there's a person next to a bus stop raising their hand. What's behind you? Any ideas? Well, the answer is there's probably a bus behind you. Yes, thank you. There's probably a bus behind you.
Could be a cab, though.
Sorry?
Could be a cab.
Could be a cab, but it's a person at the bus stop, so prior information, but at least there's something behind it this person is signaling to, right? And this idea that humans can interpret the actions of others and act in a way that's informative when being observed by others, that's what I call theory of mind, right? So it's that the double combination of skills here, which is not just being good at interpreting the actions of others, but also I can understand how you will interpret my actions. And that's crucial whenever you want to coordinate, communicate, or otherwise interact with other agents in somewhat cooperative settings. And you might think that this is so crucial because obviously we want to have systems that can do this with humans in the loop. You might think that in our favorite way of thinking about games, in our favorite way of like testing AI systems, which is games, this should be well studied. So let's look at the little grid here where we have fully cooperative versus two-player zero-sum on the y-axis, partially observable versus fully observable on the x-axis. And let's look at the popular kind of benchmarks that people are looking at in AI. So we have shogi, we have chess, we have Go, backgammon, Dota, StarCraft 2, two-player poker. All of these games are two-player zero-sum. Somehow we want to build AI systems that are really good at beating someone, but we don't want to build AI systems that are good at cooperating, which I find very, very surprising. Now, n-player poker isn't really two-player zero-sum, so some of the restrictions don't apply, but it's also not really cooperative. I would argue that it's very much not fully cooperative. In fact, if you cooperate in n-player poker, then you're breaking the rules, you could get fired from the tournament because that's called collusion, right? So there's a huge gap here in our landscape when it gets to games as we think about in AI. So what's in that large question mark here? Well, maybe we don't need it. Maybe all the interesting questions can be asked and answered in two-player zero-sum. And sadly, that's not the case. So in particular, let's forget about ad hoc coordination, zero-shot coordination. Even in self-play, the fully cooperative, partially observable setting has unique challenges. And we'll talk about that in part 1. They simply don't happen like this in two-player zero-sum. But even more importantly, and that's going to be part 2, there's something crucial about two-player zero-sum. I'm not sure if I should say crucial or pathological, and that is that all Nash are created equal, i.e. interchangeable. And beware, this is only true in two-player zero-sum. It's not true for any other problem setting. And what that means is, if you're wondering how you can learn to coordinate or compete with another agent, you don't have to worry about that other agent. You can just find any approximate Nash equilibrium, and you're guaranteed not to lose at test time. Okay, this is true for two-player zero-sum and two-player zero-sum only. And that happens to be the one quadrant where basically all of AI games research has happened in the last 50 years. And what this means is that any variant of self-play that gives an approximate Nash equilibrium can't lose at test time when matched with a stranger without having to do anything interesting at all around adaptation or And this is entirely not true in fully cooperative setting. It's in fact so not true that even a perfect self-play policy can be absolutely bad when paired with a stranger. And this is something we'll talk about in the second part of the talk. So we need fundamentally new algorithms, formalism, solution schemes for the fully cooperative case, both for self-play, but even more so for zero-shot coordination. And we want to talk about coordination with AI agents, with human agents, sorry. And that's addressed in part 2. We'll be using reinforcement learning. So we have an agent. The agent gets observations O and reward R from the world. The agent takes action U, and then we get a new state. I want to shout out something here, which is the new state S prime is sampled and it's updating dynamic from a distribution that's conditioned on the previous state and the action. But we're assuming that the transition probabilities are static, i.e. the environment itself is static, even though the state is changing. And what's really important here is that this agent can interact with this world over and over again to maximize the total expected return per episode. And I'll emphasize there's this conditional independence. I only care about the previous state S and the action U to understand the conditional probability of the new state S prime. I don't care about the policy that generated this action in the single agent case. And we'll get back to this in just a few slides. In particular, we'll be using deep reinforcement learning here because we want to scale to complex real-world problems that have large high dimensional observations and large action spaces, yada, yada, yada. So we'll be using a deep neural network that maps from observations into either policies or expected values, what have you. Because we're interested in multi-agent learning, obviously we've got to have multiple agents. So rather than just having one agent, we have the red agent and the blue and the green. And in general, in the most general multi-agent context, they would get their own observations, their own rewards, take their own actions. What makes this hard is that what happens in the environment now conditions not just on the previous state of the world and the action of the red agent, conditions in generality on the actions of all of the agents in the environment. How can we solve this? The most common and popular approach for multi-agent learning with regard to deep neural networks is called naive learning. Actually, it's typically called independent learning. I call it naive learning. And that's just pretending that other agents don't exist. So we have this wonderful world now that's augmented to contain all other agents. So from this agent's perspective, they can just ignore the presence of other agents and pretend that's a new environment. The issue is that this environment is now non-stationary because other agents are learning. It is not non-stationary like the weather might be non-stationary and changing. It's non-stationary in a world where potentially my actions at one episode can change the policies of other agents in future episodes. And that means it's not just a random fluctuation, it's a response to my actions, right? And that fundamentally changes learning problems. So when we are optimizing multiple losses, a lot of things can go wrong. Naive learning has a lot of context examples, x times my loss is x times y, yours is minus x times y, I control x, you control y. We go at infinite circles if you do independent learning. Obvious issues here. Another thing you might want to do though, is you may want to model the presence of other agents because your policy is going to change how this environment looks from my point of view. I can factor out the changing part by modeling you and then I have a stationary problem again. The issue obviously is that when all the agents are doing this, then them having a model will also change their future actions. So I should probably model the fact that other agents have a model. And you can see that this will immediately lead to this wonderful explosion of complexity, which is very typical whenever we think about multi-agent learning. Whenever you have complex agents trying to do exact reasoning over the presence, actions, beliefs of other complex agents are doing the same, we get these infinite loops. Right? This is a fundamental problem in multi-agent learning, and yet somehow humans can deal with these settings. And I think there's a lot of questions here how to deal with those loops in generality. So what do we suggest? We suggest Hanabi. And what is Hanabi? Can I have, I know you can have a show of hands here. Who knows the card game Hanabi? Can you like do a thumbs up or something? Some signal if you know the card game Hanabi. You're shaking your head there, you don't know the card game. You know the card game, that's nice. Cool. So what is Hanabi? Hanabi is a fully cooperative partial observer game, as you can see from this little plot. And in particular, it works as follows. We have fireworks. Fireworks are piles of cards that we're trying to complete. So this is what Mike Bowling calls collective counting. Okay. So I want to put my cards on these fireworks, actually want to do it as a team. The twist in Hanabi is that I can't see my own cards. Okay, so it's a fully cooperative game. We have, let's say, 2 players for now. And I'm holding my cards away from myself. So I'm holding my cards like this. So you can see my cards, I can't see my cards. And the goal now is I have to figure out how I can play the next legal card. And what legal means is I have to play the card I have to play the card n+1 on a firework of that same color when the card n has been played. So in particular, in the current situation, the yellow 2 would be playable, the red 2 would be playable, and the green 3 would be playable. But I can't see my card, so I have to receive information from you. Obviously, if you could just tell me what to do, that'd be centralized control. There'd be no communication barriers, and it'd be trivial because you just say, well, you don't hold any of the cards, what do I have? Instead, in Hanabi, communication is costly. I can only point out sets. And in particular, I can tell my friend, my colleague in this team, that they are holding either what cards are yellow, I can tell them what cards are 2s, and so on, right? So what I could do here, for example, I could point out sets. I could say the 1st and the 5th card are 2s. I could say the 2nd card is red. I could say the 1st card is yellow, okay? But I can only point out sets. I can't say this card is a 3. I would have to say those 2 cards are 3s. And they have to figure out what that means. And this is costly. It's costing 1 information token. So the challenge in Hanabi is how can we take actions that can be interpreted by other agents to mean something. It's all about theory of mind. So one example that humans do very, very naturally in this situation, I would look at my friend's hand and I would say the 1st card is yellow. Without prior agreement, they wonder, well, this card is yellow. What does that mean? Well, let me think about it. The goal of the game is to play cards. I need to know what cards are playable. So maybe my teammate is hinting to me that this card is the yellow 2, and therefore it's playable. And then they might also think, well, maybe this implies that there's another 2, so that they couldn't point out this card is a 2 and that card is a 2. Okay, and all of this reasoning happens ad hoc, right? This reasoning can be carried out without prior agreement, without prior conventions. If you just give someone the rules of the game in a bit more detail, they will figure out these interpretations. Okay, and that's theory of mind: interpreting the actions of others and finding actions that are informative when interpreted by others. So the question is, how can our AI systems learn this kind of behavior? Are there any questions so far?
Do you have teammates?
Yeah, so it's an n player game from 2 to 5. So it's one team. It's fully cooperative. I'm going to repeat: we have one payout. Doesn't matter who's playing the card. We all get a point for every card that's played legally. So when I play the yellow 2 or you play the yellow 2, doesn't matter. We get a point. So it's 25 points, the maximum number of points you can get in this game. Any more questions?
So it's also always just one hint, I guess.
You can only give one hint at a time step, or you can play or discard a card. If you're hinting, that costs 1 token, and you recover a token, information token, when you throw away a card. It's called discarding. Okay, so I can't, the hints are costly, and I have to choose to either hint or take a different action. So hints are very costly. And I have 8 hint tokens in the beginning. They're like these little gadgets here. They're roughly like this. And I pay 1 whenever I give it hint action, and I recover 1 when I throw away a card, which is called discarding, in which case that card is no longer available for me to play. Any more questions? Okay. It seems like there are no more questions on Hanabi. Everything is very clear. By the way, highly recommended. You can play Hanabi online with your friends and family. Really fun game. And it will also help you make more sense of my talks in the future. So there you go. Cool. So we published a paper here, the Hanabi Challenge, New Frontier for AI Research, which is really trying to bring Hanabi to the learning community, to the AI and machine learning community. Because there really hadn't been any work using reinforcement learning on Hanabi at that point that achieved any interesting results. And let's talk about this. Let's talk about how we can train agents in Hanabi. This is the self-play part. This is a little bit older. I don't want to say it's boring. It will tell you something fundamental about partially observable, fully cooperative systems when you think about learning agents. But I really think that part 2 is the most interesting part. So I will speed through this part 1, like there's no tomorrow. But still, like, please shout out if you get lost. First of all, what do I mean by self-play? By self-play, I mean to train a team of agents to maximize the expected return when tested as the same team. So this is very, very crucial, the same team. So for simplicity, imagine you have 2 players only, pi 1 and pi 2, and the joint policy pi consists of pi 1 and pi 2. We just want to find a pi star that's the argmax of the expected return j when pi 1 is matched with pi 2. So during training, we maximize this objective. In a test style, we're going to test pi 1 and pi 2 together. The Brazilian team is tested as a Brazilian team. There's no shuffling happening. Okay? We address the setting with the Bayesian action decoder for deep multi-agent reinforcement learning. So this is basically taking the following approach. Multi-agent perspectives are great for some problems, but sometimes it's really painful to think about in a multi-agent setting. Can we reverse and go from multi-agent problem to a single agent problem by doing interesting maths? And the answer is yes, here we can. And the answer is also, it kind of helps in this problem. And then we'll undo that again in the next part of the talk. So what does it mean to interpret the actions of an agent? So here we have Bob. Let's pretend Bob is me. Bob's holding the cards like this. So Bob can't see his own hand. And Bob has to figure out what's the probability distribution of P of the hand of Bob, i.e. his cards. In particular, given that there's Alice takes a look at the cards of Bob and then says, I'm going to discard, throw away my 5th card. So now the question is, what did Bob learn? Per se, discarding the 5th card says nothing about the hand of Bob. However, remember that there's base rule. Base rule is one of the most important things in life. We should never forget that. P of x given y is P of y given x times P of x over P of y. And here in this setting in particular, P of X given Y is the probability of the hand of Bob given the action of Alice. What can Alice learn, right? And we can fill that in here. And because we're in centralized training, this probability of the action of Alice given the hand of Bob, we can replace it with the policy of Alice in this highly simplified setting, where we now have to just calculate what was the probability of the action Alice took under the hand that Bob is reasoning about. And then we have to normalize this entire equation by the denominator. So if we look at this for a little bit, what you'll see is clearly the state S of the world is not sufficient. I have to think about the beliefs of Bob to understand the future actions of Bob. However, this belief of Bob doesn't just depend on the previous belief, the prior P of HB of Bob. It also depends on the action of Alice, as you would expect. But furthermore, it depends through the denominator on the action that Alice could have taken in every possible hand that Bob could be holding. So this fundamentally changed the learning problem at hand. Okay? Because before we had the state S prime that gets sampled based on the previous action and the previous state only, i.e. only what happens matters. Now, if you think of the state, the belief, it suddenly depends not just on the previous belief and what happened, it depends on the action pi of Alice, i.e. why it happens. This is fundamental, and it makes a lot of sense, right? If I send you a message and the message is 1, what does that mean? Well, you don't know. You have to know all the instances in which I would send a message 1 versus message 0. So it's very, very intuitive that whenever we do anything with interpretation of actions, we have to reason over not actions, but policies. And this has fundamentally and profound implications about how we can do learning in a principled way in these settings. It's not just a question of what happened, but why it happened. And what that means is we have to explore, first of all, over policies rather than actions. Taking action A means absolutely nothing unless you also specify what policy produced the action A. So this point is kind of important. Any questions on this point?
Why exactly do I need to worry about the policies again?
Go back.
Why does it make no sense?
Because the next belief of Bob, right? So the belief after Bob observes the action of Alice is a function not just of the action of Alice, but of the entire policy that generated that action. Okay. So unless I know your policy, that action is meaningless. Just think of a learning protocol. We were trying to establish some
Okay.
communication protocol, and I tell you, here's the 1. I took the action 1. What do you know about the world? You know absolutely nothing. You have
So
to
do I
know, yeah.
Do I need a belief over all of Alice's policies also?
This is centralized training. So we're assuming, it's a good question, centralized training. So at training time, you can have a ground truth access to Alice's policy at training time.
So I know it.
You know it, you know Alice's policy.
Okay. Okay, thanks.
Good question, thank you.
Just to be
More
clear, you're
questions?
saying you're conditioning on like the weights of that policy in this case?
How you do it technically is a different question, but just from a method point of view, like conceptually speaking, you're either implicitly or explicitly conditioning on the policy. You have to consider the entire policy, right?
Gotcha.
Because why things happen matters, not just what happens. Okay. And this leads to 2 answers here. First, we have to explore over policies rather than actions. And secondly, we have to compute the beliefs implicitly or explicitly for each of the policies being explored, right? So what does this mean? First of all, clearly there's something that I'm doing that's kind of silly. If you look at this, the action of Alice doesn't depend on her belief. So what's the point of like having beliefs if we're not feeding it into policies? So what we should do is we should really have a policy that considers the belief of Alice, because otherwise, if Bob doesn't have a belief, that what's the point of a belief unless you use it in the policies? But what does that mean? That now suddenly when Bob wants to Bayesian reasoning, Bob needs to condition on the belief of Alice to do the posterior updates. And this means Bob needs to have a belief over beliefs, and you can high order belief, and you can clearly see that this leads to one of these wonderful explosions. Because if I model the belief of you and you model the belief of me, we get to a recursion and it explodes. There's something called interactive probability that is going to explode even with finite number of nestings here and that. For the tiniest problems, it's a hard problem, so this option is out for us. We're going to use common knowledge. And what that means is we'll compute a belief that conditions on public information only over the private features. So in particular, you and I know everything that's common knowledge, the last actions, state of the board, The only things that are private are the hands of Alice and Bob. Okay, so my hand and your hand are private. So we're going to have one belief that captures the distribution over the hands of Alice and the hand of Bob, given all the public knowledge. That's what we call this public belief, BT. Okay. Crucially, it assigns some probability to every possible joint hand. And the second part we're going to do is, rather than exploring in the state of actions, we're going to explore in the state of policies. However, those will be partial policies because they just assign an action to every possible private hand for the acting agent. And that's what we call PyDet. It's a mapping that assigns an action U to every possible private observation. And then we'll sample this mapping. So this mapping itself is deterministic to be informative. And we'll sample this mapping to explore from a distribution over mappings conditional on the public state and the public observation. Okay. And that's what we call this PyBAT. So PyBAT is kind of a meta policy that takes in the public belief and the public observation, yeah, and produces a distribution over mappings that get sampled at training time to explore, right? Because that's a fundamental problem again, when you think about informative actions, you want to be deterministic. When you think about learning, you have to be stochastic. You have to do both, you have to sample. But clearly, if I'm random, my messages are less informative, so therefore I want to be as deterministic as possible. And that means we're going to have a deterministic mapping from private observation to actions, but we're going to sample this mapping. So, any questions on this? Maybe I keep going a little bit and then you can think about your questions in the meantime. Please speak up. What is this PyDet? It's a mapping from private observation to actions. I.e., this is an instruction list that allows you to look at my hand and look up in the list which index it is and then find the corresponding action. So if I'm holding 5 5s, you're going to discard your third card. If I'm holding 1 1 1 2 2, you're going to play the fifth card. Okay, that's what this is. We're going to parameterize the distribution over those lists given the public information. So that's a very long x-axis here that has some probability for each of these lists to be used given the public state. I'm going to learn that mapping. Okay,
how do you generate that list? You just generate it the root?
Okay, now we're going into implementation details. There's no time for that, unfortunately, but it's difficult. We did it. It works by making certain factorization assumptions. If you're interested, there's a whole talk I can send to you that captures in much more detail. I won't have time to go into implementation. It's just like at the conceptual level, I just want you to understand what this is on the method level rather than implementation in this talk. It's a good question though. Is it clear what this object is though? It's a distribution over mappings. And the distribution conditions on the public state that includes the public belief and public observation, and the mapping is learned. So distribution is learned. Okay. And then the good news is that we can now do the Bayesian update. Because we had this previous belief, BT, that was common knowledge, we had a way of generating this mapping from the common knowledge state in a common knowledge way. That means this mapping is common knowledge. The action UA, discard the third card, is common knowledge because actions are observed. And that means we know what the previous beliefs were. We know what would have happened in every single action that could have been taken. We know the action that was taken, and that means we can now cross out the impossible hands. We now know that those hands are not possible because they don't match the action. Okay, so we can now calculate the new posterior update. So what that means is we now have this wonderful picture where we are acting in the state of partial policies, and the state itself contains the public belief over private features. And indeed, we before had this decentralized Markov decision process, partially observed Markov decision problem that has a lot of issues as I described. Now we have a single agent representation. There's only one agent, and that's this PyBAT, this meta agent. The state contains a belief over the private features and the public features. The so-called action we're taking is really producing an entire list of instructions for what to do in every possible private observation that the acting agent could be in. The action U is now a latent feature that gets sampled based on the private observation. And then we calculate a state update that includes both the new public features and it includes the new belief that's computed as a posterior update. Okay, so now fundamentally we can do whatever we want in terms of single agent learning methods as long as we can deal with those very, very, very large state and action spaces, which is what we did in the paper Bayesian action decoder. Don't try it at home necessarily, it's difficult. And it took me a lot of thinking to get this right. But ultimately, this was the first time that learning method produced like a real state of the art in Hanabi. 25 points is the absolute maximum. We don't know what the achievable maximums are. we got 24 point something, 2 points here. We got the best win rate of any known Hanabi agent on Earth, around 58% of perfect games in this setting. And we were very proud of ourselves. We were like, this is so great. We did like such good work. It was so hard. It's so conceptually beautiful. Even got accepted ICML, who would have thought. And let's look at this a little bit more. We were very happy that it has these really interesting conventions. It knew nothing about anything a priori, right? This is all learned from scratch. And it learned that like hinting your yellow should be used to indicate that you should play the newest card. It found this policy that like hinting white or blue means to probably discard the 5th card. And we gave this bot to David Wu, who was the creator of the strongest heuristic bot that existed. And David Wu said, this bot is very strong in the early game, It's really quite beautiful, okay? So question, is this a success? And indeed, we haven't been lazy since, so we've done more work on this, on the self-play axis here. In particular, the simplified action decoder for deep multi-agent reinforcement learning does the same kind of stuff much, much easier. So keeping the multi-agent perspective actually makes this problem easier rather than harder. I think the centralized view is a very, very difficult way to think about the problem. And then we have a way of improving the policies further using search, which is a paper we had at AAAI, and that you gets very, very high scores, 24.6 points or something. I should say all of these things are open source. You can run them on the GPU in no time. It's all very easy and simple. But question, is this a success? Should we be happy with this result? In particular, imagine you're playing Hanabi with me. We were explaining the rules of the game. I'm holding my hand, and now you tell me this card is red, right? Would I in any way or form know that you telling me this card is red means I should play my 5th card or my 3rd card? Absolutely not, right? And indeed, David Wu said, they're very different than the natural human convention sets. So in the next part of the talk, we'll talk about how can we learn policies that you can actually expect humans to also find? How can we coordinate with a stranger rather than self-play? Okay. And I think that's really the cutting edge frontier. That's the right way to think about Hanabi. Hanabi doesn't make any sense. This is really just, we turned Hanabi, this game of like theory of mind, into a number crunching problem. That's not what Hanabi is, not what Hanabi is for, it's not what people should do. I think it's a big mistake of the challenge paper that we didn't understand these issues at the time. We shouldn't have phrased this problem as we did, because the real challenge of Hanabi is to treat it as a theory of mind problem, which is reasoning over strangers, reasoning over partially observed opponents, where you can't agree on arbitrary handshakes. And this we can approximate with a zero-shot setting. In this setting, we're training a team of agents to maximize the expected return when tested with an independently trained version. Okay, so what this means is we're going to train the Brazilian team, and then somewhere else in the world, we're training the Argentinian team. And there's a wall between. There's no information exchange during training time. But at test time, we're going to throw those two teams together. Okay, so we're going to test them in a zero-shot coordination setting where they play one game together without any prior exchange. They can't coordinate. It's called zero-shot coordination. And only the score in this one game matters. To make it a little bit more tractable, the coaches can agree on a training strategy beforehand. And the question is, what should the strategy be? So this is a pretty hard problem. It looks easy because you have this objective. You just want to maximize the score that the Brazilian and Argentinian team get when you mix them. However, you can't optimize it because you're not allowed to evaluate this objective during training because it's a zero-shot coordination problem. And it's easy to tell after training that you failed, but there's no known scalable algorithm that solves this problem in general. And I will give you a little instance of a very simple tutorial problem that illustrates why this is so hard. We made a little step in that direction in a paper called Other Play for Zero-Shot Coordination that was published at ICML. Again, I should always say all this work is done with amazing collaborators in a cooperative effort. I think learning, multi-agent learning is also applicable to multi-agent learning itself because writing papers is a cooperative effort in a team that sometimes involves communication challenges. And here's the formal problem definition. So suppose that multiple independent AI designers construct agents that have to interact in various but ex-ante unknown deck probabilities without being able to coordinate beforehand. What learning rules should these designers agree on? This applies to every problem we think about in the world, because there are other agents that are partially or entirely uncontrolled by you. So you have to ask yourself, what solutions can I expect them to find? What solutions do they expect me to find? When you're doing self-driving cars, Tesla has to interact with other cars. if you own Tesla shares, you may hope that Tesla gets 95% market share. There's always going to be human drivers around. There's always going to be other cars around, and they have to coordinate in zero-shot fashion, right? They fundamentally can't have complete access to each other's policies. They fundamentally have to find policies that work with partially known agents. And the policies I showed you so far in self-play setting do not have this property. So this is hard even in the simplest cases. Let's imagine the following. You are playing a game with a random stranger on the internet. And in particular, you need to cooperate by choosing one of the 10 levers shown on the left-hand side. It so happens that if the two of you pick the same lever, both of you will get the reward that's shown next to the lever in the image. Okay, so if you pick this one, you get 1 point, both of you. If you pick that one, you get 0.9. If you pick this, you get 1 point, both of you. Furthermore, you get nothing if you pick different levers. And you have a single attempt with this random stranger, then you'll get matched with a different random stranger. And the task description is common knowledge. This entire rule setting here is common knowledge between two strangers. So you know that the random stranger is going to see exactly the same task description here. Okay. The question is, what should you do in this setting? What lever do you play? Any answers? What do you do?
Point 9. You play the point 9.
Why?
Because it's the one that stands out. And you'll get point 9 instead of however many, 1 over how many ever levers there are. Yeah. But of course, then you need to think that the other person has the same strategy.
Mm-hmm. So any counter suggestions? Anyone else? Any ideas? What would self-play do? What if you trained, multi-agent learning on this self-play? What would they do?
The top one. It all picked whatever fixed one. Self-play would pick a random one of the one, but always the same one.
Right. So self-play would pick an arbitrary one of those levers. Right. So if you understand this, you understand something very fundamental about the challenge of cooperating, coordinating in a zero-shot fashion. Right. So let's go through like little thought experiments here. I think what we all just did basically is we first of all replaced the random stranger in our minds by a twin copy of ourselves, an imaginary twin. So it's me and my imaginary twin. And we go through solutions basically. We're modeling this question of, well, let me just pick an arbitrary 1.0 lever. And because my arbitrary twin is an exact copy of me, it's going to go through the same reasoning process, right? So we're going to be like, oh, let me pick an arbitrary 1.0 lever. So I'm going to pick this lever here. My imaginary twin is going to pick that lever. Whatever, right? Anything could happen. And clearly, when we went through this, it doesn't work. That's miscoordination, and the expectation is like 0.11, whatever it might be. So next option. Let me pick the 0.9 lever. And my imaginary twin goes through the same reasoning process because they also discarded that previous option. And now suddenly we can both coordinate and we get 0.9 in expectation, right? And question is, how can we bring this to multi-agent learning? How can we formalize this? And the key insight here is symmetries. Symmetries exist in the world. Symmetries are abundant in physics. They exist in image recognition problems, what have you. And the idea is you have some mapping phi. You have some function phi that acts on states, observations, and actions. And it so happens that if you jointly apply this mapping phi from an entire set of possible mappings phi to states, observations, and actions, the topology of the problem is unchanged, right? And that means that the conditional transition probabilities, the reward function, and the observation function are entirely unchanged in their structure when you shuffle around. You can think of phi as permutations, and when you shuffle around all of the different nodes. And because we apply to all parts of the point P, we can just apply to policies itself, where we have this policy now acting on the permuted action space and the permuted observations. Okay, this is pretty abstract, so let me give a little example here of what's going on. You have a robot, and the robot is standing at the position X and some XY, and the goal is in the middle, and we're assuming that this room has some symmetries. And that means that if I invert the y-axis, I can ask, is the position down here equivalent to the position up here? Well, clearly it isn't, because if I take the green action, the first action if you want, the robot is moving away from the goal here, but it would be moving towards the goal if it moves upwards here. And that means I have to both invert the axes and I have to exchange the action space, because then the green action will maintain the same semantics That's where this topology structure comes in. Am I getting closer or farther away from the goal? And what's crucial is when we have those symmetries, then we can do some very, very interesting work. In particular, let's think about what do these phi's correspond to in the lever game. Phi's are just permutations of the levers, okay? And because I have this equivalence mapping here, in particular, the reward of a policy pi and the reward under a permutation has to be exactly the same, because, you know, tau and phi tau are equivalent once I permute the actions and the trajectories. So therefore I have this equality where like j of pi equals j of phi of pi for all symmetries. So in the lever game, what do these phis do? The phis do nothing but simply permuting the joint action of the two agents. So if the two agents were picking this lever before, all the levers are equivalent, so there's a symmetry between these levers. Therefore, the phi1 here, for example, permutes this action to those levers, right? And there's a phi2 that permutes these actions to down there. And you can see that the reward is unchanged in this lever game. But what's important, I'm applying phi here to the joint policy. I'm applying phi to the actions of both agents. Does that make sense? And that keeps the reward exactly unchanged. What do these phi's correspond to in our algorithm now? They're crucial, because what it means is that while in self-play I can optimize both sides of this equation of pi1 and pi2 exactly, in other play, I have to be robust to making arbitrary decisions differently from how I did them. Okay, I can only specify my partner up to the equivalence class of equivalent policies, i.e., what this means specifically. If I think this lever that pays 1.0 is great, I have to be robust to you assuming any of the other levers that pays 1.0 is just as great. And crucially here, I'm not applying phi to pi1 and pi2, I'm applying phi only to pi2. And what this does is that it lets us maximize the expected return in an equivalence class. So if I can only specify my imaginary twin up to the equivalence class of policies, then this objective corresponds to the expected return when randomly matching two partners in the equivalence class. And other play indeed in this setting is the best possible meta-equilibrium. That's the solution algorithm we should agree on. And note two, if the symmetries are known, if you know what things are equivalent, then other play can be implemented on top of any deep RL algorithm. Okay. Any questions on this? So very quickly, what is other play as a picture? I'm no longer training the Brazilian team in its original constellation. At training time, I'm going to train the Brazilian team with the randomization permutation of the other half of its own team. I'm also doing the same with the Argentinian team. So these teams are still trained independently. But then at least at test time, when I match them together, they will both be trained in a way that is robust to symmetry break. Okay. Does that make sense?
Knowing the symmetry is a pretty big assumption, isn't it?
Depends on the problem. I mean, in general, this would be a graph isomorphism. So you could argue that this is a hard problem. Typically, actually, when we provide problem descriptions to humans, the symmetries are contained in the problem description, right? So you'd say all the colors in Hanabi have certain properties, so it's very evident from the problem description. I think it's difficult to recover once we represent the problem as as an RL environment where you have states and actions and returns. It's clearly there, but it's difficult to recover. So this gets to an interesting question: how can you do this in generality? Yes. More questions? Good question. Thank you, Vanderlyn. So if you're confused, can you just tell me what you're confused about? There's nothing wrong with being confused. What's bad is being ignorant and not trying to fix it. Ignorance is not a problem.
I think you have a typo.
Okay, that's good. Where is the typo? I probably have more typos.
Your maximization is over pi1, I think, and not over pi.
Really? Where? Here?
The max, yeah.
No, it's argmax pi. Pi is a joint policy. So when I said that before, pi is a joint policy that includes pi1 and pi2.
Pi is equal to pi1 and pi2.
Yes. Okay. Heavily abusive notation, but this is just what it is. Pi is a joint policy. I normally use bold pi, vector pi to be pi 1 and pi 2, but this is just what it is. So pi is pi 1 and pi 2. Okay, it's a joint policy. More questions? Anything that's unclear? Is anyone still confused? Let's talk about what this does in Hanabi. Yeah?
One question, how much does this increase the number of training samples that you need to converge?
It doesn't actually, at least empirically so far it hasn't. You know, it's one of the things where it depends on the problem in general. I can't make a general statement here, but in our case, it has an increased number of training samples. It has just led to different solutions. So let's talk about symmetries in Hanabi. In Hanabi, all the colors are equivalent. These are just labels, arbitrary labels. Obviously, you have to play the yellow 2 onto the yellow 1, but playing the yellow 2 onto the yellow 1 is the same semantically as playing the green 2 onto the green 1, right? So you can't be colorblind. You have to regard the colors in actions and observations and so on and all the trajectories, but they're arbitrary labels, okay? And zero-shot coordination means there are no arbitrary labels. You only have the structure of the problem available to coordinate on. You can't put arbitrary labels on things, okay? And that means all the colors are equivalent. Therefore, permutations phi of all the colors, including fireworks, cards, action space observations, are equivalence mappings. So what does that mean? Let's look at an example here. Phi is a mapping where we exchange the yellow and the white colors. Okay, so one agent will see the original game where there's a yellow 1 here and I can play the yellow 2 and I can hint for that by saying your first card is yellow, right? But the other player will observe a permuted version of this and they don't know what the permutation is, right? They'll just get the result of this permutation. So in this world, the white 5 became a yellow 5, so the fireworks are reordered. And the hand of the partner, or their hand now, has a white 2 there. But you should notice that the semantics and the action now is different action. The action now is your first card is white, but that first card is still the playable 2 for that color. Okay, so you have to permute the actions, observations, and the state. Okay, and then the semantics stay unchanged. If you permute, so what this means is doing phi on the joint policy is a no-op. It will reshuffle all the colors, but nobody cares because it's like sampling a different game. But the crucial part is we're not doing phi, we're not doing domain randomization, which people do on like joint policies on the environment. We're doing asymmetric randomization across arbitrary differences. So only one of the agents is going to observe at every episode a different sample of phi. Does that make sense? And the results of this are rather astonishing, I should say. So first of all, in the matrix game, it does pretty much exactly what you would expect if you've been following this talk closely, which is at training time, self-play looks much better because it gets 1.0. So here, this is our Hanabi papers that I showed you in the first part. We're congratulating ourselves because we get these very high performing policies. And we're like, this is great. We're so smart, right? Such good number crunching. And if you look at other play, that gets 0.9 in contrast. However, at test time, other plays still get 0.9 and self-play gets 0.11, whatever you have, right? And that's because the other play solution exploits the fact that these things are always symmetric, so you can't coordinate on them, but this thing is different. And in Hanabi, that transfers exactly. In particular, in Hanabi, coming up with an arbitrary color code, all the different ways of doing arbitrary color code, where blue means X and red means Y and what have you, right? There's a very, very large space of those that are all equivalent, but mutually incompatible. And those are all the different high-performing 1.0 solutions that if you could exactly coordinate on, would give you high returns in an easy way. And those are the only things that our self-play agents will ever learn. So if you look at the SAT agent by itself, the simplified action code I mentioned before, that gets around 24 points in expectation in self-play. But when you match different seeds, it gets 2.5 points. That's awful, right? Now, when we add the other play algorithm just by itself, that already raised the cross-play score to around 15 points. So when we now match independent seeds, that is much better. And now we can add more regularizations. Here's an auxiliary task where we do hand prediction, what have you. And this now gets us a cross-play score of 22 points. Okay? And you can see this in the policy. So if you just look at the SAT agent, you have this conditional action matrix where UT plus 1 is yada, depends on UT. And you get these arbitrary color mappings where different colors mean different things. And then obviously in a different run, if you run that same thing again, there's an arbitrary choice to be made. These colors mean very different things. What's interesting is obviously in the matrices, you see that they play well with themselves, but they don't play well with independent runs. So these are 11 different seeds we trained for the simplified action decoder. And you can see that they can coordinate with the exact copy, but they can't coordinate with an independent run. Now, clearly, if you can't work with an independently trained version of yourself, if me and my imaginary twin don't manage to solve the problem, I cannot expect to solve this problem with anyone else in the world. Does that make sense? So self-play is fundamentally broken, okay? We should not be doing self-play ever if we're interested in coordination problems. It just so happens that that's what everyone's been doing for like 30 years in this domain, right? And these problems only come up in these fully cooperative, none of this shows in 2 player 0 sum, right? Which is why these questions have been entirely ignored, which is very hard to, like, it's very difficult to imagine at this point that these questions haven't been considered before. And yet that's the best, that's true to my knowledge. And you can see that the SAT agent here actually has this fully built-in matrix where it's very compatible with others. Now, this would be cool if this was the result, but there's a little bit more, and that is the question now, given that we have this other play mechanism, can we find policies that are more human compatible? What I mean by that is policies that can coordinate with a human in a 0-shot setting, where there's a single game of a human being matched with an AI agent. And the answer is yes. I wouldn't be building up so much if this wasn't the case. But here we get a little scatter plot where each of the plots is one deck of hands. Decks change the hardness of the game drastically in Hanabi. And on the x-axis, you see the self-play bot, and on the y-axis, you see the other play bot. For the vast majority of games, the other play bot gets a higher score. It's around 16 points average. Like, just keep this in mind. Like, think about the number a little bit. 16 points on average when paired with a human. The human knew nothing about this bot. We just selected for humans that were good Hanabi players. And yet we can discover policies that are compatible with human policies without ever having played with a human at training time, simply by thinking about self-consistency through this other play mechanism and by considering 0-shot coordination. Right. So we're not done. I think this is the very first step on a long road. I hope many more people get excited about this because I think it's very fundamental. And when then asked about this, well, if you don't know the symmetries, well, you know, humans can discover reasonable symmetries without being provided the symmetries, but then humans don't start with the assumption of having just access to states, action observations. I think we're thinking about problem representation, right? Next question is, can we adapt on the fly? So humans are really good in Hanabi actually to adapt to a broad range of policies in a single move. Turns out that, you know, self-play agents find policies that even humans can't adapt to. It takes many more games to understand what the heck they're doing because they are so arbitrary and weird. And I think what this hints to is, you know, if you think about understanding the problem and solving it as 2 problems. When we do self-play, we are learning about the problem space while finding a single solution. And that fundamentally is inappropriate for coordination. We have to understand the problem surface, understand the structure of all solutions, and then decide what are the compatibilities, incompatibilities, and so on and so forth, right? And what this hints towards is, can we learn other play or similar algorithms? I think other play seems kind of hand-coded. I want there to be something that's more learned, be it through evolution. So I encourage all of you, think about this. Again, there's a matrix game here where you can test your ideas. It's all open source, it's all linked out in 30 seconds. And so far, I yet have to meet a person that comes up with a proposal that works and it can't be refuted in the matrix game, right? So I encourage you to think about, if I don't know the symmetries a priori, how can I find the 0.9 lever in the matrix game? We've open sourced all this code because I think this journey should be made as easy as possible. The Hanabi learning environment is open source, and Hanabi search is open source, simplified action code, and we will open source the other play code in the future. With that, I'd like to thank you all for listening and open the floor to questions if there's time. I'd love to hear more about what's unclear. Thank you all.